Morning, everyone. Morning, Hike. Morning, Kimmeline. Morning, Sammy. Morning, Ava. Morning, Nikolai. I'm not included with human. What am I? Hi, Azra. Hi, Logan. Hi, Charlie. Good morning, anyone else who's watching. Starting off in period B today. Taking a look in classroom, see what's anything new, anything different. Got a daily post we'll go through in a second. And I can see, I'm a G, okay. If we taken the wrong way. I see that scratching the surface is due tomorrow before midnight, 11:59 p.m. So we will have scratching the surface hopefully done before midnight tomorrow. Alright, extend section is kind of long, but the evaluate is quick. So if you take a little extra time today, going into tomorrow, you'll still probably be fine. Finish on time. Morning, Ryan. Fun fact today. A supervolcano in Maine erupted during the late Paleozoic era, and that is what provided New England with its granite. We got a lot of granite hundreds of millions of years ago. So late Paleozoic period. Go back to our clock. Right here, probably around 300 million years ago, when we had kind of like the beginning of vertebrate land animals, animals with a backbone. And they don't have dinosaurs. Ah, there we go, dinosaurs. So several, probably like million years before the first dinosaurs, there's a supervolcano that erupted where Maine would be, the continental crust where Maine would be, and all that eruption of lava and magma became igneous rock, and granite is a type of igneous rock. So we have a lot of granite in New England, especially in Rhode Island, New Hampshire, Maine, but granite is an igneous rock. There's three types of rocks: igneous, sedimentary, metamorphic. Sedimentary are made up of different sediments, different layers. Metamorphic is pressure and squeezing, like marble. Sedimentary rock, like sandstone, if you remember studying ancient Egypt. Crushing of the sand, pressure of the sand out in Egypt. And then igneous, made from lava. Igneous, ignite, to ignite, cause fire. Granite is one type rock, but there's no volcanoes around, except there used to be. Hundreds of millions of years ago. Which is pretty cool. Just to kind of think about. And this is an link to the study that was done in 2019 about this supervolcano. Real advanced words. This is an actual published document by a team of scientists. So this is what an actual study looks like. This is not an article. Well, you don't have access to this article. This is a study. This is not something on CNN or Live Science or Scientific American or Science News. This is the actual study itself. Morning, Rainey. Alright, so virtual classroom today. Zoom out a little bit. Oh no, come back. Alright. We're going to review quickly the explain questions from Scratching the Surface. After we do that, answer any questions you may still have. We'll go into introducing this interactive mantle sim in the extend section, and that's going to help you answer the next 3 extend questions. So we do need a model to help us answer those questions. Models linked in the extend section. And then it goes into a little bit about earthquakes. What in the mantle allows us to view the different layers from an earthquake. And then the extend section has a couple more questions. We finish it, and then we'll finish the evaluate tomorrow. Turn it in for midnight. Can't stop, Nikolai. I mean, look at it. It's just like being back there, right? Yeah, I like the class pet. You know, little spirit rover. Remember, you can click here. Those of you who are watching later, you can click those to get links to Remind and to YouTube. Alright. Explain section. Pretty much did this one with you guys already together yesterday. Reminded you from last year that pressure is the amount of force over, which means division, a given area. Okay, you could think of like even density. Density is the amount of mass over a given volume. So pressure is a ratio. It's force over area. Okay? The bigger the force, the more pressure you're going to have. The smaller the area, the more pressure you're going to have. Okay? How can you increase force? Well, you can either increase gravity. You can't really do that unless you're adding mass to a planet. Or you can just add mass to what you're doing, and that will increase force. Force is weight. Weight is a force. Okay? Your weight can change by going to a different planet. Your weight can also change by losing mass. Right? Mass does not change unless you lose it. So, to kind of visualize this, I had this fraction here. 2 divided by 2 is 1, right? I could make the area become smaller, so 2 over 1, and then pressure increases, becomes a 2. Or I could do, instead, 8 over 2, increase the force dramatically. 8 divided by 2 is 4. Either way, I increase this number right here, which is pressure. So it's a ratio, it is a fraction. If I increase force, I increase pressure. It's a positive relationship. If I decrease area, I increase pressure. That's a negative relationship. They're opposite, right? So, reminding you of pressure because it deals with these layers here, right? 2, which layer of the Earth experiences the greatest pressure? Well, it's going to be the layer that's the most interior to the planet, because it has all the layers above it pushing down, plus the Earth's atmosphere. So, what layer would that be? You go all the way down, that would be the inner core. Has all these layers pushing down by gravity, pulling the sun of the Earth, plus the atmosphere above. So the inner core is going to have the most pressure. All right. So depth and pressure have a positive relationship, right? If I increase depth, I'm going to increase pressure because I'm increasing the amount of mass that's above it. So I'm increasing force. All right. So everything's increasing: force, mass, pressure with depth. All right. That's why I had you guys research depth. I didn't really want to focus on thickness. All right. You could figure out depth by adding the thickness of each layer before it, but I think it'd just be easier just to look for depth. Okay. So the deeper you go, the more pressure there is. All right. Think about swimming to the bottom of the deep end of a pool. You start feeling the pressure on your inner ear of the water pushing down on your head. All right. It's the same deal. Outer core has a little less pressure. Mantle has less pressure than that, and the crust has the least amount of pressure with just the air of the atmosphere pushing down. Right? So it goes from greatest to least: inner, outer, mantle, crust. Which layer experiences the least? The crust. How do you know this? Because there's no other layers on top of the crust. Only the atmosphere is on top of the crust. Okay? And the atmosphere is definitely the least dense of all the Earth's layers. Alright? If you were wondering what is the... Where am I looking? Right here. The asthenosphere is the upper half of the mantle with the crust. This is where you're going to see a lot of plate tectonic action. We'll get to that towards the end of this document. Right? The lithosphere is the crust and uppermost solid mantle. So the mantle does have kind of like an almost solid state that's at the very top. So lithosphere, litho meaning rock. So the rocky sphere. Alright. Oops, went too far over. 3. You can refer to your research. That right there, I could give the depth of the inner core, depth of the outer core. That would be referring to my research, citing. 3. How does the pressure experienced by each layer relate to what state of matter that layer experiences? So if you would answer this question in a little more simpler terms, you would do well in this answer. Why is the inner core a solid? So referring to, I'm leading you to that the inner core is a solid and the outer core is a liquid. Why are those what they are? Alright? Why is the outer core a liquid? Why is the inner core a solid? So the outer core is a liquid because of the pressure being high enough to make it higher than the melting point of iron and nickel. So there's iron and nickel in the outer core. So the temperature in the outer core is higher than the melting point of iron and nickel. Okay? Why is inner core solid? Because there's more pressure than in the outer core to the point where those iron atoms, the most dense metal, or the densest metals, just there's a lot of iron, are at the core, and there's not enough space for them to move around as a liquid, so they're stuck, squeezed together as a solid core, solid inner core. Okay? These atoms are packed nice and tight together, and they can't move because of pressure from all directions by gravity and all the other layers pushing up into it in all directions. So it stays a solid. Alright? Because it retains its own shape. So again, from last year. Will we get points off if we don't refer to our research in question 2? Referring to your research would be obviously, providing to me the order of the layers. That's also part of your research. Would I take points off? Probably not. I'd probably take a half a point off for you not telling me the why. Which layer experiences the least? How do you know this? This could help you answer the why. That's why I kind of put that there. So, I going to take points off? No, but if you don't do a good job of doing this, I'm going to take a half a point off. Each one of these is worth 1 point, right? So you telling me this is worth, you telling me this right here, you telling me the order is half a point. You telling me this is half a point. This is to help you do that. Good question. For, let me ditch that for a second. How does density, it's probably the harder one, how does density affect the composition of each layer of the Earth? Tell you go to ptable.com, look for iron, look for nickel, okay? Atomic number 26, atomic number 28, iron, nickel. Compare their position to magnesium, calcium, silicon, and oxygen. Why do I ask you to look at magnesium, calcium, silicon, and oxygen? It's because those are the common elements that make up the very upper part of the mantle, that lithosphere, and most of the crust. There's other elements, but those are the primary ones that are going to bond together to make different compounds that make up minerals and rocks. If you look at p-table, you compare their densities, clicking on the elements, okay, you find out that iron and nickel are more dense than magnesium, calcium, silicon, and oxygen. So now, give me a relationship. Well, just like the deeper you go, the more mass there is, the more pressure there is. The deeper you go, the more dense the layers are. The materials are more dense. Okay? So what happens? Layers and density, or I should say, depth and density have a positive relationship. Depth should be, I'm referring to depth there. Deeper you go, the denser the layers are. And so, pressure and density determine the layers. And that's the big takeaway I want you to have in this explain section, to get from this explain section. Keep going to that website. It's the same picture though. Pressure and density determine the layers. Pressure and density, right? So density is going to separate the layers, just like a density column in a graduated cylinder. Again, if you don't remember what that was, I just literally Googled density column. It is probably the most common 7th grade lab demonstration you can think of. Oil, alcohol, oil, water, soap, milk, maple syrup, corn syrup, honey. Put a bolt in there, ping pong ball, all kinds of densities of regular and irregular shaped objects, different liquids, all separate on their density based by gravity. The Earth is the same thing because the Earth was once molten. The Earth was entirely a liquid at one point, when all the pieces were accreting together, when the sun was accreting and becoming the sun. There was different spheres starting to pull together more material, and because of all the energy, it was a molten Earth. And because of that, the heavier metals sunk down to the center of the Earth, and the less dense material stayed at the surface. So the Earth became a density column in its early stages. Once it was older and started to cool, pressure then took over to create the different states that we see. So the crust cools, very light material. The mantle has semi-molten, solid rock that's convecting back and forth from the hot core, and the core is really hot because of all the pressure. Okay, outer core is a liquid, even though it's metal, because of all the matter that's sitting on top of it, pressing down. Inner core is a solid because those atoms have nowhere to go, and they're stuck as a solid shape. Even though it's incredibly hot, and there's more pressure than the outer core. Okay? So it's all about pressure and density. That's what sets up the layers. That's what's going to determine the different geological features that we see across the Earth. Different phenomena, like an earthquake, or why our crust moves. If you have any other questions, send them to me throughout the day. I want to get over to the extent section. So we have convection in the mantle. This is the largest, the thickest layer of the Earth. Therefore, it's going to have movement from the warm core to the cooler crust. The crust is brittle. It's not very dense, so it breaks very easily. When you have two currents aligned together, that's where you're going to break crust apart. And when you do that, you push crust away. When you push crust away, you create what we call tectonic plates. The movement of heat from a warmer object or area to a cooler or area with less heat, less thermal energy. It's called heat transfer. Convection is the heat transfer that takes place as a result of currents. Convection takes place within a fluid. Large amounts of heat are transferred through Earth via convection currents. Some of these currents are in Earth's liquid outer core. Other convection currents are present in the mantle. Convection currents in the mantle form and transfer heat as rock slowly rises toward the top of the mantle. So this is incredibly slow. This is not like the homemade lava lamp you made at the beginning of the year. The rock is still hard, but it flows very slowly like a fluid. As the rock rises, it cools and sinks back down into the mantle. As with all convection currents, convection in the Earth's mantle is the result of three things: heating and cooling of rock material, changes in the rock's density, and the force of gravity. Because it is not possible to directly observe the mantle, it's under your feet, and it's incredibly hot and a lot of pressure to get down there, we'll never get to the mantle. Scientists sometimes make models to study how this part of the Earth moves. Based on the findings, they make inferences and draw conclusions. So, how do they even know that there's a mantle to begin with if they can't see it? How do they know there's an outer core? How do they know there's an inner core? How do they know the outer core is a liquid? How do they know the inner core is a solid? We want to use this model to understand that and understand earthquakes, because earthquakes gave us the evidence that there are 4 layers and they have different states. So you can go ahead and click this sim if you haven't already done so. Directions are here. If you don't see them, just zoom out a little bit. And if you want to get rid of them, you can just zoom in. But when you're here, sim's going to start. It's showing you the outer core. It's showing you the mantle. Light colors are hot. Dark colors are lack of thermal energy. If you right click or 2-finger click on your Chromebook, you will transfer thermal energy away. If you hold left click or 1-finger click on your Chromebook, you'll add thermal energy. And that's all we're going to focus on to start. Eventually, we will pause to talk about earthquakes. So, single click, left click, and holding adds thermal energy to the mantle. Add thermal energy for a minute somewhere in the mantle, halfway between the outer core and the crust. So let's kind of look at this question. What happens to the surrounding currents, like the hot upwellings and the cooler sinkings? What happens to the currents on the far side of the planet in the mantle? So we're just going to hold it down for a long time. Just keep a minute in your head, okay? Somewhere halfway between the crust and the outer core. You just hold down, single click, left click, and just watch what happens to the surrounding area and then the area on the far side of the planet. So I'm going to pick right here. So we have 4 upwellings coming from the outer core. Just holding it down. Any major observations yet? Anybody in chat who can answer quick? from where we started to where we are now, what has happened? Remember, there were 4 upwellings coming out of the outer core, all kind of equal distant from each other. Where are all the down drafts? Where is all the sinking happening? Well, you did make a new convection current, Nikolai. That's right. But can you describe the pattern? All the sinking is happening opposite where you're clicking. Doesn't matter where you click. Other people try different spots and hold it down. You've made a new overall current, yes. All the rising, all the upwelling is happening where you're clicking. If you've noticed, all the upwelling kind of moves to the point. Maybe occasionally there's one on the opposite side of the planet, like you kind of see right there. However, all the black, all the cooler sinking, kind of curls around and gets pushed to the side. And it sinks on the opposite side of the planet. When you align upwelling currents in convection, you are pushing the edge of the mantle away from where you're clicking. So I'm adding thermal energy, I'm aligning convection currents together, I'm pushing the mantle away, and I'm causing it to sink back on the other side of the planet. You understand that? That is causing a current across the entire planet. It's pushing the mantle. Because of this, anything that's floating on the mantle is going to follow this current. Just like a boat in the ocean, when we did ocean currents, this upwelling, literally, is moving the surface current away. And so you would have crust moving this way and this way. So what happens to the surrounding currents, like the hot upwellings and the cooler sinkings? Okay, the upwellings align where I'm clicking, and the cooler sinkings happen on the opposite side of the planet. The entire surface of the mantle is moving away from each other from where I'm clicking. It's dividing. It's dividing. And so question 6 is then now the opposite. 2-finger click or right click if you're on a PC or Mac. And holding transfers thermal energy away, so adds coolness that doesn't exist. Remove thermal energy for a minute, again just kind of eyeballing time, keeping it in your head. Halfway between the outer and the inner, outer core and the crust. Okay? What happens to the surrounding currents, like the wellings and the sinkings? What happens on the far side of the planet? So you're just doing the opposite of number 5. So I'm going to let this refresh because the currents have been all mixed up. Give it a little push. There we go. So now I'm just going to hold and transfer thermal energy away. A little slower than last time, but you can start to see those sinking denser materials are aligning, just like last time, and as it falls to the outer core, it's not as dense as the outer core, so it doesn't go into the outer core. It flows around the outside of the outer core and pushes those upwellings to the other side of the planet. And when you have the upwellings align, you create a dividing boundary, and it's going to start pushing the mantle to where you are removing thermal energy. Keep adding, or removing thermal energy, and it pushes the upwellings to the other side of the planet. And they're aligning where I am holding down removal of thermal energy, which is causing more material to push more of the warm material out of the way. So what happens to the surrounding currents? The colder, denser material pushes the hot upwellings away. This allows the colder downdrafts, the cooler sinkings, to align where I'm holding my mouse, my cursor. Not everyone has a mouse. This causes upwellings to happen on the opposite side of the planet, the far side of the planet. So I created a combining boundary. It's where material was coming together, right? Here I create a combining boundary. Materials coming from here and then down, materials coming from here and then down. I'm creating something called a combining boundary, or in geology, we call this a convergent boundary. So if there was any crust floating on the surface of the mantle, it would be moving across the top, and colliding. Boom. Whereas over here, crust is moving away, moving away, moving away, moving away. It's dividing. If you had two continental pieces of crust, so two land masses colliding together, it's where you're going to get mountains. If you have ocean crust, so sea floor, colliding with land crust, the denser ocean crust is going to slide under the less dense continental crust. That's called subduction. Maybe you remember hearing that from the vocab probes. When that happens, some magma from the mantle gets trapped between the two plates, and the mountains that form can become volcanoes. That's what happens out in the West Coast. The Sierra Nevadas, the Cascades. Mount St. Helens erupted, what was it, 30, 40 years ago, a couple days ago? Out in Washington State. Or Oregon, I can't even remember. Washington State. So there's volcanoes in the United States. Out in the Pacific Northwest, the western side of the country. I don't want to buy one, I just want to see one. All right here. This is a convergent boundary. The denser Pacific plate is slipping under the less dense North American plate. where Nikolai is. And what's happening is part of this less dense crust gets bumped up into the air, and volcanoes can form because some magma gets trapped as one plate goes under the other. One piece of crust that's cracked goes under another piece of crust that cracks. Okay? Down in Southern California, you get a lot of earthquakes because they're not really they're converging, but they're slipping past each other. It's called a transform boundary. It's where they're sliding past each other horizontally. That creates a lot of friction. You get earthquakes. We'll get to earthquakes in this section. Right? So I'm throwing at you a lot of geological terms. Wish we had more time. I'm just trying to give you a crash course. And it comes from these two questions. Right? You add a lot of thermal energy, you're going to create a dividing boundary. You take thermal energy away in the mantle, you're going to create a convergent boundary. You've had 6? Are you in Northern or Southern California, Nikolai? Small ones, right? Because I haven't heard anything in the news. Average, yeah. Well, it's a good thing you're still safe. Alright, and so if I go back to that map, convergent, that means there's a sinking current happening between these two pieces of crust. Anything fall off the walls? I hope not. So let's get into some of these earthquakes. Okay, hitting backspace pauses the model so you can click and drag to add thermal energy or remove it throughout the mantle. Try adding thermal energy to all the cold sinking currents or remove thermal energy from all the hot rising currents. Can you ever make the entire model reach equilibrium? That means the same temperature. And stop convection. Hit backspace. And I'm just going to paint in You guys hear me? Lost my mic. Desktop audio too, but at least you guys can still hear me. You gotta do one or the other. Don't do both like I just started to do right there. Color in any... Okay, good. Color in any dark or remove any light, remove any thermal energy, or add thermal energy. As best you can. Hit backspace again. Can you make it go to equilibrium? Can you make the model go to equilibrium? Even if you remove all the excess thermal energy or you add in thermal energy? The answer is no. But the why is pretty important. even if you fill all in the dark spots, the cold, or you remove the excess heat, you still have a colder crust and a very, very warm outer core. And these two differences in temperature are what is going to cause a convection current. Because remember, you need a change in temperature to create a current. Whether it's wind, whether it's convection, whether it's this in the mantle, you need a difference in temperature. High temperature to low temperature. If you don't have that, you don't have a current. So you can't just get rid of the current and say, haha, I did it, I broke it. No, there's still a difference in temperature and the current will still form. It may be in a different spot, it's still going to form. Okay? Next three are about earthquakes. All right? And so this kind of shows you, again, how seismographs can measure earthquakes. Okay? Machines that are free in the air and can monitor the ground moving because they're attached to it. Hitting space pauses the model and adds a blue triangle that acts as a seismograph, which is a tool that geologists use to measure seismic waves inside the Earth. So, energy inside the Earth. Two plates move, collide, shift. It's going to create an earthquake. Right? So I'll go back here. I'm going to reset it. And I'm going to let go. Space, pause for earthquakes. Right click, you can change where the seismograph goes, but we're not going to do that. Left click initiates it. So, space, boom. Okay? There's the seismograph. So there's Coventry, Rhode Island. This right here is what the seismograph reads. And it's just putting it here in the outer core just because you can see it because it's white hot. All right? It's not there because the outer core is rippling. This is just like a view of what the blue triangle sees. You gotta understand that. This black line is just what the blue triangle measures and sees. All right? So it's what it's going to draw. It's going to make waves. It's going to take the energy from the Earth and translate it to waves on paper with a crest and a trough and a wavelength and a period and an amplitude, just like last year. Clicking anywhere in the mantle causes an epicenter, so the start of an earthquake. The seismograph presents all seismic activity on a line in the core of the Earth just so we can see it. It is not actually in the core. Just keep that in mind. All right? So you hit space, you pause it, the seismograph's up at the top, and we're going to cause an earthquake near the blue triangle. Describe over time what you see for number 8. So we're going to do it somewhere near. So somewhere in this convection cell right here, click and cause an earthquake. And so you could say initially that there was very strong, you can even screenshot it. I was a little slow, but you could have screenshot the seismograph. And you could include that in number 8. A picture is worth a lot of information. So the waves are very strong at first, but then weakened over time. So there was a very strong amplitude that weakened over time. There was a high frequency, high amplitude that slowly weakens over time. But notice that it ripples all across the Earth. It doesn't just stay in that one part. High amplitude, high frequency right there, and then it weakens over time. These ripples travel around the outer core to the opposite side and all throughout the mantle. So describe what you saw. You can do it again. Describe what you see. Refresh the whole model. Again, space, click to cause an earthquake, but do it on the opposite side of the blue triangle, opposite side of the seismograph, and give it a longer period of time. There we go. Space. I'm going to go opposite the blue triangle, opposite the seismograph. So now we're going to be, I don't know, somewhere out in the Indian Ocean. India, Nepal. We're going to cause an earthquake. What happens over time? Will we, on the other side of the Earth, pick up seismic waves from this earthquake? These compression waves. We sure do. Are they as strong as when they were right next to the seismograph? No. The amplitude was much smaller, but we were still able to measure the amplitude from that earthquake on the opposite side of the world. This is how geologists were able to start to study the mantle, the outer core, and the inner core, because they set up seismographs all across the world, and scientists talk to each other and share information freely. They started to coordinate their data at different points all across the planet, and they measured seismic activity. They measured earthquakes. Really, really strong earthquakes will ripple the entire mantle. Notice it doesn't ripple the outer core. The outer core is much denser than the mantle, and those waves don't ripple the outer core because the outer core is much denser. And so they looked at other types of waves, and they saw that some waves could actually travel through the outer core, and these waves couldn't. And so they determined the outer core had a different density than the mantle. They discovered the core. A little more research, a little more information on these earthquakes, and they figured out there was a solid inner core. Do seismic waves travel through the core? No, they don't, and I think I already led you to the answer. So that would be the end of the extend. Long section, very involved, and we're going to go over it again tomorrow, because the evaluate is quick. So if you have a couple that kind of aren't very complete, you obviously can have a little time. When we review it tomorrow, to finish up during the review tomorrow, and prep yourself for the evaluate. Alright? So, today, just worry about the extend. It's a lot of information. If a couple you leave, I don't want to say completely blank, but just lacking a little bit of detail, you forget, you're confused, we're going to go over this section again tomorrow. And then the rest of the time you're working on these questions right here. The evaluate. This is tomorrow. You are stopping here today. Alright? See you, Nikolai. Be safe out there with diseases and earthquakes now. Got questions throughout the day, send them through Remind, send them through email. Hi, Ryan. Today, 4:32 though, Eastern Time, NASA is launching SpaceX is launching a rocket carrying 2 astronauts to the International Space Station. First time we've had American astronauts ride an American spacecraft since 2011. Pretty cool. Probably put out the link for streaming around 4:30. Alright? Historic. Gotta wear the NASA sweatshirt today. Alright? See ya, Hike. Rest of you, again, if you have questions, send them to me throughout the day. Do nothing around 4:30. Up on YouTube and search SpaceX or NASA, and I'm sure they'll have a feed of the launch. Alright? See ya, Hud. See ya, Rainy. See ya, Charlie. Bye, Donnie.